All right, so we will continue with the norm definition, but about the discussions over here about finding the P matrix which converts one representation into another. I would like to give you a simple clue which might help you. So in understanding why this is the case, so let's A be a matrix, and I will write down the columns of A. Okay, so let this be the first column, let this be the second column, and let that guy be the nth column. This, okay. And if I have, let's say, a beta vector, which is a n by 1 vector, so this b1, b2, and bn coefficients over here. So if I have a times b, okay, so if I get this guy and multiply it by, let's say, once again, if I write down a times beta, which is equal to, let's say, this, c1, c2, cn, beta 1, beta 2, beta n. So these coefficients is actually going to multiply each the corresponding column of the A matrix. So the result is going to be, so this m by n is m by 1, result is going to be m by 1 vector, and that is going to be simply equal to, let's say, I can write that as summation I from 1 to n beta I ci, right? Or maybe we can say it like this. So this will be equal to beta 1 c1 plus beta 2 c2 plus beta n cn. But it's going to be n by 1 vector times b. So this is m by n. This is n by 1. And a times b is also n by 1. So if this is, maybe this will help you to understand it a bit easier why we write that the coefficients is the columns, and write down the coefficient of the basis vectors in those columns and multiply the same coefficient of the base vectors with that column to get the second representation. So if I try to write it down for clarification, but if it confuses you more, you can skip that. Don't worry about it. All right, so let's continue with another definition, and that is the definition of comes with the second part of our lectures in the first chapter. So we will be talking about the definitions of norms. Okay, norm linear space. I'll also change the color for that. All right. So in the norm definition, we will be talking about distance. So let's see how it goes. So consider the linear space V with a specified field F, and our field is either real numbers or the complex numbers, and we will be defining a function for every vector x, and we denoted that function as norm of x, that assigns to each vector x a non-negative real number. Okay, so it can be 0 or positive, but it cannot be negative. So the norm of a vector is always non-negative, and that can be defined in different ways. So there are multiple norms in the vector space that you can think about, but the norm is a function is called a norm if it satisfies the following properties. So the first property is also called the triangle inequality. So norm of x1 plus x2, if you take two vectors in your vector space, the norm of their summation should be less than or equal to the summation of the individual norms. And the second property is that if you take any vector and multiply it by a scalar in your field, the norm of the resulting vector is equal to absolute value of that scalar times the norm of the original vector x. And the last property is the norm of a vector x is equal to 0 if and only if the x vector is equal to 0. Otherwise, so which means that any vector in our vector space other than the 0 vector has a non-zero norm. Okay. All right. So the expression norm x is the read as the norm of x, and this denotes our norm function. And with the norm definition, our vector space with the corresponding field, so this triplex definition, the vector space, the associated field with the vector space, and the norm definition actually constitutes a normed vector space. It's a norm space. Okay. And what do we understand from a norm is that, so it actually defines a distance in our vector space. So if I'm given in two vectors, let's say x1 and x2, so the norm of the difference of x1 and x2 gives me the distance between those two vectors. Okay, and note that so any vector of x can be written as x minus the 0 vector. So the norm of x is for every vector is actually the distance of that vector to the origin. Okay, so now we can define the distance of every vector to the origin by using norms. By the way, later we will add the not only the distance information, we will continue with building up our algebraic structure further, so that we can talk about the geometry of that space in means of angles. But that will come into the play when we will be talking about the inner products and so on. Okay, we will see that later. But the important thing is that, so once you think about if when you can define the distance of the vectors to the origin, for example, you can define unit poles in the vector space, right? So, for example, you can define, let's consider the 2 norm, okay, which we will see in a second. And if you would like, we would like to find, for example, all the points in the R square whose distance to the origin is equal to 1. For example, if I take the 2 norm, which I will give definition soon, then we will see that all these points actually lie on a circle. Okay. So a set of all the points with norm equals to 1. And I can define different norms, and I will end up with different shapes here corresponding to the norm, etc. Okay, so let's see with an example and proceed accordingly. So let our vector space be the R square with the associated field, the real numbers R, and let X be the any given vector in R square with the elements alpha 1 and alpha 2. And here is a one candidate function which is denoted by norm 1, and it says that the norm of any vector for this two-dimensional space is that absolute value of alpha 1 plus absolute value of alpha 2. And the question is that thing a norm or not? Okay. So for this definition, to be a valid norm definition, it needs to satisfy three properties like P3, P2, and P1. Okay. So let's start with the last one, let's say P3. And P3 states that if norm x is equal to 0, then that is satisfied if and only if x is equal to 0. Okay. So notice that I put like I wrote down this like a two direction arrow there. So I need to prove in the forward direction and also in the backward direction. Okay. And in the backward direction, for example, let's start with the backward direction. So the backward direction claims that if x is equal to 0 vector, then its norm is equal to 0. So this is backwards direction, and let x be the 0 vector, 0, 0, both alpha 1 and alpha 2 is equal to 0. Then what is norm of x according to that definition? That is equal to absolute value of 0 plus absolute value of 0, and that is equal to 0. So we were able to show in the backward direction. Okay. And in the forward direction, so this is because it's the if and only if statement. It says that if norm x is equal to 0, then x must be equal to the 0 vector. All right, so let's write down the conditions for norm of a vector with that definition being equal to 0. Means that absolute value of alpha 1 plus absolute value of alpha 2 is equal to 0. Okay. So you know that the absolute value function takes non-negative values, right? So this is a non-negative number. So this is non-negative. And that second term is also non-negative. And I am summing up two non-negative numbers and their sum is equal to 0. So that is only possible if both terms are equal to 0, right? The first term is equal to 0 and the second term is equal to 0. And if absolute value of alpha 1 is equal to 0, then alpha 1 is equal to 0. And if absolute value of alpha 2 is equal to 0, then alpha 2 itself is equal to 0. So which means that x is equal to 0. So that is the 0 vector. Okay, so we were able to, by showing in both directions, we proved that if and only if statement in P3. So it says that the norm x is equal to 0 if and only if x is equal to 0. Okay, so please be careful in the exams or in the quizzes, etc. If you are given an if and only if condition, you need to prove that in both directions, forward and backward. So let's continue with P2. It says that if you take any vector and any scalar in the field, the resulting vector, when you multiply the vector with that scalar, its norm of the resulting vector should be equal to the absolute value of the scalar times the norm of the vector. So let's see if that applies to our definition over here. So let me try to write maybe a bit down here. So P2 states that if you take a scalar gamma and multiply it with the x, that should be equal to absolute value of gamma times norm of x for all x in V, and for all gamma in F. Okay. So let X be equal to alpha 1 and alpha 2. Then gamma times X is equal to that vector where we have gamma times alpha 1 as the first entry and gamma times alpha 2 as the second entry, right? And if I compute the norm of gamma times X, that will be according to that definition over here. It will be the absolute value of the first term plus the absolute value of the second term. So it will be equal to absolute value of gamma times alpha 1 plus absolute value of gamma times alpha 2. And that is equal to absolute value of gamma times absolute value of alpha 1 plus absolute value of gamma times absolute value of alpha 2. And I can further write that thing as absolute value of gamma times, in parentheses, absolute value of alpha 1 plus absolute value of alpha 2. Which means that I was able to write down the norm of gamma times X as the absolute value of gamma times, sorry about that, my lines are getting worse and worse, times norm of X. All right, so we were able to show that thing as well. And the next thing is the triangle inequality. Okay, so I will continue with P1. And what was P1? The triangle inequality states that norm of x1 plus x2 should be less than the sum of the individual norms. So let's write down norm of x1 plus x2 should be less than or equal to norm of x1 plus norm of x2. So, okay, so let's define x1 as that x1 be equal to alpha 1, alpha 2, and let x2 be equal to beta 1, beta 2. Okay. And if I write down x1 plus x2, it will be the vector alpha 1 plus beta 1 and alpha 2 plus beta 2. And the norm of x1 plus x2 is equal to the absolute value of the first term plus absolute value of the second term. Absolute value of alpha 1 plus beta 1 plus absolute value of alpha 2 plus beta 2. And by using the properties of the absolute values, the definitions, I can claim that this first term is less than absolute value of alpha 1 plus absolute value of beta 1. And the second term is also less than absolute value of alpha 2 plus absolute value of beta 2. Okay. So this because the absolute value of sum of two terms is less than or equal to the absolute value of the sum of individual terms. Okay. Sum of the individual absolute values. And notice that this is simply equal to absolute value of alpha 1 plus absolute value of alpha 2 plus absolute value of beta 1 plus absolute value of beta 2, which is basically norm of x1 plus norm of x2. Okay, so we were able to show that x1 plus x2 norm is less than or equal to norm of x1 plus norm of x2. So all three conditions are satisfied. So therefore, this is a valid norm, and this is called the L1 norm actually. So this is L1 norm. Do you have any questions? So if not, let's continue with the other examples. So the second one is the norm definition, the distance definition, the Euclidean distance definition that you are familiar with. So this Euclidean norm also satisfies the axioms of norm, properties of norm. So this is actually called the L2 norm, or it's also called the Euclidean norm. Norm. And this is a valid norm, so let's say yes there. Okay. And the next norm example is also an interesting definition. So you have x as alpha 1 and alpha 2, and it says that this infinity norm of that thing is the maximum of the absolute value of its entries. Okay, so you compute the absolute value of each entry and you pick the maximum of that, the bigger one. So this is also a norm. It is the infinity norm, L infinity norm. So the answer to that question is also yes. And all these norm definitions that we have seen, that L1 norm, L2 norm here, that can L infinity norm, they are actually called P norm. Okay, so all these norms can be generalized into a family of norm definitions, which is called the P norm. Okay, so as you see, when P is equal to 1, so you see, so this is norm P. So as you see over here, so norm x1 is according to this equation, absolute value of alpha 1 plus absolute value of alpha 2, and norm x2 norm of x is equal to square root of absolute value of alpha 1 square plus absolute value of alpha 2 square. And how about the infinite norm? So can we show that as p goes to infinity, we will have this definition, maximum of the absolute value of the entries. So as p goes to infinity, our claim is that we end up with the infinity norm, and the definition of infinity norm is that you get the maximum of these elements. So we can see why this is the case, maybe by working on an example. So let's say x is equal to 2 and 10. Okay, the first entry is equal to 2 and second entry is equal to 10. Sorry. So let's compute the L1 norm of x. Okay, so L1 norm of x is, according to this definition, absolute value of 2 to the power 1 plus absolute value of 10 to the power 1 to the power 1 over p, which is equal to 1, and that is simply equal to 12. Okay, and norm 2 is of x is equal to absolute value of 2 squared plus absolute value of 10 squared. Sorry, 10 squared, and we compute its square root of 2, right? So this is something like this is 4 and this is 100, and after terms like the square root of 104, right? So let's continue in that manner. So let's try to write down the L3 norm. then what we will have is the absolute value of 2 cube plus absolute value of 10 cube to the power 1 over 3, right? And as you see, the first term is something like 8, and the second term is 1000. Okay. By the way, it's not something like the 8 itself. But the thing is that, as you see, when you take the higher and higher power of these terms, the second term in the summation dominates the others, right? So if I take the infinity norm of that guy, like xp, and if p goes to infinity, let me write down the expression. That's going to be simply equal to the power of p plus 10 to the power of p, and we take the power of 1 over p. So as p goes to infinity, we can neglect the first term. Okay. The first smaller term, right? The smaller term. Smaller term. So this can be neglected. Sorry about that. And if you neglect the small term, then you end up with 10 to the power of p divided by to the power of 1 over p. Then you get the absolute value of the larger term over here. Therefore, the infinite norm of that x is the maximum value of absolute value of the entries over there. Do you have any questions? So infinite norm is also a p norm, so that's also a valid norm. So these are all can be written as forms of p norm, L1 and 2 up to infinity. They're all valid norm definitions. Okay, so as I said before, we can also define, once we define the distance concept with the norm, we can also define a sphere in our vector space. Okay, let's write that. So we can define, let's say, sphere in our vector space V using the norm concept. Why we said that the norm of any vector is the distance of that vector to the origin, right? So if I say that, so let's define a set S sphere, okay, such that it's composed of the vectors in our vector space where norm of V minus, let's say, something V0 is less than a certain number R. Okay. So those points on S defines actually with center V0 and radius R. And we can also try to plot the unit spheres by using the different norms. Okay, so let's consider R square for the time being. Okay, and Let's define sphere first for the L2 norm. Okay. So you would like to find the points where the norm of x is equal to 1. Okay. Where x is equal to alpha 1 and alpha 2. Okay. So with the norm 2 definition, you will have norm x2 is equal to square root of alpha 1 whole square plus absolute root alpha 2 square to the power 1 over 2, and that thing being equals to 1, right? So we would like to, let's see, okay. Then all these points where you have alpha 1 square plus alpha 2 square, the square root of those summation being equal to 1 lies on a circle in R square. Right? So this is the, let's say, set S that is composed of the vectors where the norm of x is equal to 1. So let's investigate the L1 norm as well. So let's try to plot the L1 norm. And we would like to look for the points where L1 norm of x is equal to 1. So definition of the L1 norm was the absolute value of x1 plus absolute value of x2 being equal to 1. And so we can plot this function of this x1 and x2 being equal to 1 for in different quadrants, right? So what I'm saying is that that expression is actually, let's say like this. This implies that x1 plus x2 is equal to 1 when x1 and x2 are greater than 0.
Alfa 1, alfa 2 olacak da karışıklık olmasın.
All right. Thank you very much. So we can say this is alpha 1, alpha 2, alpha 1, alpha 2, alpha 1, alpha 2. Thank you very much. Okay, and so if alpha 1 is less than 0 and alpha 2 is greater than 0, let's say, so it will be minus alpha 1 plus alpha 2 is equal to 1. Okay. And you can continue for all the quadrants like that, but I can plot those lines over here. For example, alpha 1 plus alpha 2 being equal to 1, when alpha 1 and alpha 2 is greater than 0, it is the line that passes through 1, 0 and 0, 1. So maybe I should put it in a different color once I plot it. So I will do it like this, through the line. I will change the color. Okay. And in the second quadrant, when alpha 1 is negative and alpha 2 is positive, that is this line over there. And if you continue for the other quadrants, it goes like this. Okay. So for my bad drawing, and actually those points are like plus 1, minus 1, minus 1, plus 1. Yeah, the arrows there, right? This is alpha 1 and alpha 2. And when you think about infinity norm being equal to 1, so infinity norm says that norm of x infinity is equal to 1. So maximum value of absolute value of alpha 1 and alpha 2 is equal to 1. So this is satisfied when either alpha 1 or alpha 2, one of them is being equal to 1 plus minus 1, and the other value is changing between plus minus 1. Okay, so that then this maximum value is going to be 1. So I can show you maybe in that sense. For example, consider this line over there. Maybe I should pick another color once again. So let's make this guy. Oh, sorry. So let's make this guy green. So every point on this line, suppose it ends up with x plus 1, minus 1 and plus 1. So these are the points in the form of the second alpha 2 is equal to minus 1 and alpha 1 is changing between minus 1 and 1. And norm of that points is equal to 1 with the infinite norm. Okay. And if you continue in that way, for all the points, sorry, all the points over there. So all the points on this line is that the first entry is equal to 1, the other entry is changing between minus 1 and 1. So the maximum of absolute value alpha 1 and absolute value alpha 2 is equal to 1. The same is here and the same is there. So I can write that thing as, so this was norm x L1 norm being equal to 1, and that thing is infinite norm being equal to 1. So these are the unit spheres in your R-square with different norm definitions. Okay, so by changing the norm definitions, all of them's distance to the origin is equal to 1, but the definition of distance is changing when I'm changing norm definition. Okay. This is norm. And I also had it in my previous slides that I can show you these unit circles for different values of p. So for that thing, I need to switch to another presentation, the slides. So sorry for the white screen all of a sudden, if you're not blind. So this is actually the unit spheres for different LP norms. Okay, so L1, L2, L3, L4, L10, and you see like when 10 is 7p is equal to 10, it already resembles some sort of a square, and as p goes to infinity, that will be a solid square corresponding to the unit sphere with respect to the infinity norm. Now I can go back to the lecture notes. So were you able to see the animation now? Or...
Şu an bir şey paylaşılmıyor görünüyor hocam.
Öyle mi? Kusura bakmayın. Şunu hemen düzelteyim.
Yok gördük hocam. Bir öncekini sormadınız.
Ha, evet, beyaz ekran gözüktü değil mi?
O göründü.
Tamam. Ben ne gördüğünüzü bilmediğim için arada kaçırıyorum, kusura bakmayın. Şimdi siyah ekran gözüküyor değil mi? Yes, hope for that. Hı?
Evet hocam.
Tamamdır. Ders notlarımızdan devam edelim. Okay, so we've seen all these valid norm definitions, all the LP norms that we've seen so far were valid P norm definitions. Now in our next example, we have a counterexample. Let's say, let's define this P1 over 2 norm by using this LP norm. So this P norm is valid for P values greater than 1. And I can find as norm x1 over 2. This is a 1 over 2. As I will compute 1 over 2 power of the first term, the absolute value of alpha 2 power 1 over 2 squared. So x is equal to alpha 1 and alpha 2 once again. And the question is that definition gives us a norm. So if we can find a counterexample where the one of these axioms of the norms is not satisfied, then we can say that that is not a valid norm definition. So both P1, P2, and P3 has to be satisfied. So one thing difficult to satisfy for a valid norm definition is the triangle inequality. So we can start from that one maybe. So let's check P1 and try to find a counterexample. So let's check P1. So the P1 was the triangle inequality, saying that norm of x plus y is less than the sum of individual norms, norm of x plus norm of y. And now I will write vectors x1 is equal to 0 and 4, and x2 is equal to 9 and 0. So according to this definition, I would like to compute the norm of x1 plus x2, which is the norm of the vector. This is the 1 over 2 norm. The x1 plus x2 is equal to 9 and 4. It's 1 over 2 norm. So I will compute the square root of the first term, 3, and I will compute the square root of the second term, is equal to 2. 3 plus 2 is equal to 5 squared, that is equal to 25. Okay. But notice that with the same definition, norm of x1 is equal to, simply it's going to be itself 4, right? So you get squared and then square, so it's going to be 4. And norm of x2 is equal to 9. And as you see from there, so the norm of x1 plus x2 is larger than sum of individual norms. So this is the violation of the triangle inequality. Of the triangle inequality. Then this guy is not a valid norm. All right, so lastly, I will define the norms on function space, and we can continue from there. So I will just write down the definitions. So I'll write it below there. Norms on function spaces. So let us consider the functions f such that f is defined over the interval 0 and 1 up to a real number, and that satisfies the condition integral 0 to 1 absolute value of f of t to the power p dt is less than infinity for 1 less than infinity. And in that case, we can define norms as follows. So norm fp is defined as the integral from 0 to 1 absolute value of f of t to the power p dt to the power 1 over p. And I will write down spatial cases and today's lecture. So when p is equal to 1, you get this integral of the absolute value of the function dt. This is called the L1 norm. And sorry, when p is equal to 2, you simply compute the integral of the absolute value squared of that function in that interval and compute its square root. And this is, as you might already remember, this is related to root mean squared concept, right? For the errors that we use that very frequently. And the infinity norm of a function in a similar way can be defined as the maximum of that function in that interval. I mean the absolute value of that function, and that's called the L infinity norm. Okay, so in the next lecture we will repeat our concepts on norms, and we will restart from this norms on function spaces, and then continue with the norms defined for the matrices. So that's the end of the lecture today. So I will stop recording, and if you have any questions, I can try to answer as well. So sorry.